In this project, our goal is to build a classifier to predict loan default and improve the F1 score. We started with exploratory data analysis to better understand the data before building any model. We visualized the target distribution and confirmed that default cases are much fewer than non-default cases, which immediately told us that handling class imbalance would be important. We also examined categorical variables such as education level, home ownership, loan intent, and prior loan defaults. By calculating default rate across different groups, we saw that certain categories clearly have a higher default probabilities. For examples, borrowers with previous defaults are more likely to default again. To improve, we engineered new features that better capture the relationship. We create loan to income to measure heavy repayment burden is compared to income. We also create loan intensity to combine income percentage and interest rate, since higher interest rate amplify repayment difficulty. We use log transformations to income and loan amount to reduce skewness and make the data more stable for modeling. We also turned the previous default history into a binary feature called previous default flag because past default is the strongest predictor of future defaults. After feature engineering, we consider three models: logistic regression, random forest, and XGBoost. Logistic regression is simple and easy to integrate, but it is a linear relationship, which is too restrictive for financial data. Random forests capture nonlinear patterns, but do not always perform well when the data is highly imbalanced. XGBoost performs best overall because it effectively captures nonlinear interactions, handling many features well, and allow categorical weighting. Since dataset is imbalanced, we use scale post weight to penalize mistakes on default cases more heavily, so the model pays more attention to the minority class. In addition, we did not rely on default 0.5 probability cutoff. Instead, we searched across different thresholds and select the one that maximizes F1 square on the validation set. A common default threshold in imbalanced dataset is 0.5, so we adjust the threshold to improve it. Also, we also tuned the hyperparameters such as max depth, subsample, co-sample by tree, learning rate, and regularization strength, and use early stopping to prevent overfitting. Overall, tuning both model parameters and the decision threshold led to a noticeable improvement in validation of F1 square compared to the baseline model. To assess and improve model fit, we used stratified train test split to ensure that the class distribution remained consistent in both training and validation sets. This is important because a random split might distort the proportion of the default cases. During training, we monitored validation log loss across boosting rounds. We observed that the validation loss decreased steadily and then leveled off. We did not find a large gap between training and validation curves. If training loss kept decreasing while validation loss increased, that would indicate overfitting. Early stopping helped us to prevent from that happening. We also looked at the confusion matrix to better understand what kind of mistakes the model is making and what they mean in real business terms. In a loaning setting, if the model predicts that someone will not default, but they actually do, that's a serious financial risk for the bank. On the other hand, if the model predicts that someone will default, but but they have repaid, we lose a good customer and potential revenue. So it is not just being accurate overall. It is about balancing these two types of mistakes. That's why we focus on improving the F1 score, since it helps balancing precision and recall. We also examine how precision and recall changed as we adjust probability threshold. And we select a threshold that better reflects the bank's risk tolerance instead of just using the default of zero point 0.5. If you had more time and resources, there are several ways that could further improve the model. First, we can find more external information such as CPI and unemployment rate. These factors influence repayment behavior and could help the model better capture the overall risk. Second, instead of relying on a single train test split, we will have used stratified k-fold cross-validation to get a more stable and reliable estimate performance across the multiple data splits. And that's how we monitor the performance and detect the data drift. That's all. Thank you.